Okay. Hello, everyone. I'm Surud More, and it's a pleasure to be back again here to convey these particular set of lectures on gravitational lensing. Um, I started off with this series of lectures with an introduction to gravitational lensing and the basic equations which govern gravitational lensing. Then yesterday you heard from Anuprita, who told you a little bit more about strong gravitational lensing and how the equations that we had derived previously, how they can be used in order to learn about the matter distribution in galaxies, especially when there are multiple images forming, and you can study the properties of these multiple images, such as the locations where they are formed, then their individual magnifications, as well as the time delays coming from these images. Right? So we had derived the formulae in the first set of in the first lecture. And the second lecture, you saw how they can be used in order to learn a lot more about the universe. In this third lecture, I'm going to talk to you about weak gravitational lensing. So this is a slightly different form of gravitational lensing, nevertheless, but it's less majestic than the strong gravitational lenses that you are used to. And so, but nevertheless, very useful and very powerful. So let me introduce that to you. So before we begin, again, let me show you this picture of gravitational lensing happening within a galaxy cluster. So you can see these foreground galaxies, these elliptical galaxies, which are in the foreground. And then the background galaxies, which are getting lensed. So you can see these arcs. Sometimes there are these radial arcs that you also form here as well, here, right? Sometimes you see these merging images, where two images which are of the same object are forming very close to each other. And even here you can see this image and this image. It's a pair of merging images. Right? So this is all beautiful, right? Lots and lots of stretching and multiple images being formed. But the topic today will be of galaxies which are just weakly distorted. Okay, so these galaxies are very well aligned along the line of sight to this cluster, and that's why they get these multiple images. But if you're not very well aligned, if your beta is very far away from the object that is causing the lensing, then you don't form multiple images. Instead, you form just a single image, but it's a little bit distorted, not as the distortion is not so large that it causes arcs, but nevertheless, you see some tiny distortions, some changes to the shapes of these galaxies. And it is these changes that we are going to try to focus on. So what is weak gravitational lensing? Okay, so I'm showing you this cartoon picture of what weak gravitational lensing does, and then we'll get to the equations behind it. Okay? So what you're seeing here are pictures of galaxies, which you can see in the observed sky. Right? So these galaxies are actually located in the distant universe, like here. Right? And this is the picture that you see eventually on the sky. Right? Because that's the projected picture that you see. Now, each of these galaxies, let's consider this blue galaxy, which is here. So that particular galaxy, there are bundles of light rays, right, which are coming from these galaxies, coming from different portions of these galaxies. So these bundles of light rays, they travel towards us, and then they encounter some matter distribution in between, right, like these wisps, ghost-like structures that you see here, which are the dark matter distribution, which is supposed to represent the dark matter distribution. So it encounters this dark matter distribution, and then these bundles of light rays, each of them gets deflected by a slightly different amount, right? And so when these deflected light rays eventually come towards you and you see them in the sky, then what happens is that the bundle of light rays that started off, it doesn't remain the same bundle. It gets a little bit distorted. Right? And so the shape of this galaxy, which you see here, originally it should have looked like this in the absence of dark matter. When there is lensing which is happening, after that, the shape of that galaxy has changed. It has rotated it has stretched a little bit, and so on. Right? Similar thing happens for this galaxy, this galaxy, these galaxies. So all these background galaxies, they get distorted. Their shapes change as they come towards us. Right? And this lensing, this distortion in these shapes, it's happening because of the presence of this dark matter. Now, lensing is also sensitive, most sensitive to the structure which is roughly halfway in between us and the source. Okay? So these galaxies, when they will get lensed, they will be most likely due to lenses which are some roughly halfway in between. That is where lensing is most efficient. Okay? And so what it means is, if you look at the shapes of galaxies as a function of different distances away from us, then they will be sensitive to the matter which is roughly halfway in between them and us, but closer and closer to us or further and further away from us, depending upon where these source galaxies are, right? Depending upon the shapes of the galaxies that you are considering. So if you have some way of identifying roughly what is the distance of any of these galaxies that you observe in the sky, and you look at their shapes, then you can do a tomographic reconstruction of the matter which is in between us and them. So for example, if you look at the shapes of galaxies which are really far away, they tell you the distribution of matter here. Instead, if you look at galaxies which are here and measure their shapes, then that tells us about the distribution, which is a little bit halfway in between those galaxies and us, right? So by doing this kind of analysis with galaxies at different distances, you can do a tomographic reconstruction of the dark matter. Okay? So this is what lensing allows us to do. Okay? So to look at how to actually do these things, let's look at the important equations that we have already studied. You heard about a few of them yesterday, and then I had covered them day before, right? So the first of all, everything that you need to know about lensing, you can derive from this quantity called the lensing potential, right, given by psi. So this is related mainly to the surface density, right? This kappa of theta is called a convergence. And this convergence is just the surface density divided by the critical surface density. The surface density tells you about the mass distribution in the lens plane, right? And the critical surface density, it is a function of the distance to the lens, the distance from the lens to the source, and the distance to the source itself, right? So it's a geometric factor that gives rise to this quantity called the surface density, in addition to constants like c square and g, right? So you combine these distances and the fundamental constants, you get out a surface density. That surface density is called a critical surface density. So kappa is just sigma divided by sigma critical, and that is how you, using this particular equation, you can define something called the lensing potential. The deflection angle is just the gradient of this lensing potential. Right? This is again something which we had derived. We had worked out from first principles what the deflection angle looks like, and then from general relativity, right? And then from there, we worked out what is the definition of a potential, which will give you the deflection angle when you take a gradient of it. Right? So these were the two equations. And then there is a relationship between this lensing potential and the kappa itself, right, which is causing this lensing potential. That relation is given by the Laplacian of psi is equal to 2 times kappa. So this is a Poisson-like equation. Right? So you can see the similarity between these equations and the equations that you are familiar with. So there is a gravitational potential, right? You take the gradient of the gravitational potential, you get a force, right? And then if you take the Laplacian of the potential, then you get back the density itself, right? So there is a commonality and similarity between these equations, right? So one is a 3D equation. This is just an equation in 2D. And that's the reason why there is a log here instead of a 1 over r that you're used to, okay? Good. So then once you have this deflection angle alpha, then it allows you to figure out if there is a source which is at a position beta, then where will its image be, right? So if you know alpha, if you know the deflection angle, then given a source position, you can figure out where is the image position. So that particular equation is just geometry. And I showed you that it looks something like this. Beta, which is the original position, is theta, which is the position where the image forms, minus alpha of theta, which is what is the exact deflection that happens at that particular image position. Right? So beta is theta minus alpha of theta. This is just represents the geometry of the lensing configuration. And once you know the alpha value, then you can add a beta value, a given source position. You can figure out where the image position should be. Okay? Then the next thing that we had also looked at is the definition of a quantity called the shear, which tells you how bundles of light rays coming from a source, how they get distorted. Right? So we had worked out using this lens equation. We had taken something called the Jacobian of this equation by doing a differential, so del beta by del theta. Because this is a vector equation, there are two components to this vector in the plane of the sky, and that's why for the Jacobian you get four components. So del beta by del theta has four components. That gives you a matrix, right? And that matrix looks something like this: 1 minus kappa minus gamma 1, minus gamma 2 minus gamma 2 here, and then 1 minus kappa plus gamma 1. And I told you what this Jacobian matrix does. So you can split this Jacobian matrix into these two components. There's a 1 minus kappa times an identity matrix, which is just telling you that you take a source, it will just get magnified isotropically by a factor 1 minus kappa. Okay? And in addition to that, there is this component. Now, this you cannot write it down as some number times an identity matrix. So each of these axes are being scaled in different manner, and that's why these components look different. And so this shear component, it tells you something about how a circular source gets morphed into an elliptical source. Okay? So let's try to understand that a little bit more. So this quantity gamma, as we said, it has two components, gamma 1 and gamma 2. So it becomes easy to express it as a complex number. Okay, there is nothing complex about it. The only reason why we are expressing it as a complex number is because there are two components to it, and we want to keep track of both these components. Okay, so this gamma can be written as gamma 1 plus I gamma 2. Okay? And if you go from the source plane and if you had a circle with a radius r, then when you convert it into an image in the image plane, so as you will see it, then it turns out to be an elliptical, just like the one you are seeing here. Right? And the major axis of this ellipse is given by the semi-major axis and the semi-minor axis of these ellipses are given by these quantities. Okay, so r divided by 1 minus kappa plus mod gamma and r divided by 1 minus kappa minus mod gamma. So this is the major axis, this is the minor axis. Right? So that's how these things get stretched. And this mod gamma is nothing but the modulus of the complex number that we defined before, right? So it is gamma 1 plus I gamma 2. And so mod gamma is square root of gamma 1 square plus gamma 2 square. Right? So now we know, if you know the magnitude of the shear, what are the axis ratios that you will have, right? So if you have a source which is circular, it will get mapped into an ellipse. And the ellipse's axis ratios, they will depend upon this value of mod gamma. Right? So if you look at it, you can take this quantity and you can write it down as r divided by 1 minus kappa. I can take it out times 1 plus mod gamma. And then for this one, it becomes 1 minus kappa, 1 minus mod g, sorry. And this mod g is then defined as mod gamma divided by 1 minus kappa. In most cases for weak lensing that we will be considering, kappa will be much smaller than unity. And so for all practical purposes for weak lensing, this mod gamma will be exactly equal to this mod g, okay? Because kappa is small. So in that case, you take the axis ratios. So you can take the axis ratios by dividing one by the other, right? And you will see that it is equal to 1 plus mod g divided by 1 minus mod g. And so you can rearrange this axis ratio equation to get what is an expression for mod g. So the modulus of the of the shear itself, right, is given by the ratios of these ellipticity components, right? So, or sorry, the axis ratios b by a modified in these particular. So if you know mod gamma, then or if you know the axis ratio, then you can figure out what is mod gamma, right? So if you had a circular source, it becomes elliptical because of lensing. You measure the semi-major, semi-minor axis. You define what is this b over a, and you compute a quantity which looks like this. It will tell you how much shear it should have undergone, right, in order to become elliptical. So this way you can map out the shear at different locations in the sky. So you take galaxies at different positions, you measure their shapes. When you measure their shapes, they tell you about the shear itself, which is present on this sky. Okay? Once you know the shear, then you know the lensing potential. Good. So then we can also figure out, so I told you about what is this mod gamma. Now let's try to understand what is the direction in which these galaxies get stretched. And in order to do this, you just have to do a simple eigen analysis, right? So eigenvector analysis. So let's suppose that the eigenvector is oriented along the direction 1 and tan phi, the eigenvector of this particular matrix, right? So the eigenvector of this matrix, it will tell you in which directions you see the semi-major and the semi-minor axis, right? And so in order to do that eigen analysis, what we can do is you can take the matrix, you multiply it by a vector. So let's suppose the eigenvector is in the direction some 1 tan phi, right? So that gives you, so let's suppose that eigenvector has an angle which is phi with respect to the x-axis. Then the vector along that line is 1 comma tan phi. Right? And so you take the matrix, you multiply by 1 comma tan phi, and it should give you back the eigenvector times, the eigenvalue times the eigen. So you can compute what the eigenvectors are. One of the eigenvectors will look like this. The other eigenvector will be 1 minus kappa minus mod gamma. Okay? And so let's consider this particular eigenvector and ask what is the relation of phi with gamma 1 and gamma 2. So you take this equation and you just write it down. So this is 1 minus kappa minus gamma 1 minus gamma 2 tan phi is equal to 1 minus kappa plus gamma times 1. Right? So that's all the equation that I've written down. The second equation is something which gives you exactly the same quantity. So we'll just look at the first one. Right? And so you can rearrange this to figure out what is tan phi. And tan phi comes out to be this. And using the identity for tan 2 phi compared to tan phi, which is given by this, you can show that tan 2 phi is given by gamma 2 divided by gamma 1. So the phase of this complex number, right, it should be 2 phi, right? So you can write down gamma as mod gamma times e to the I2 phi, right? And that e to the I2 phi is just cos 2 phi plus I sine 2 phi, right? And so if you take the ratio of gamma 2 by gamma 1, you should get tan 2 phi. Right? So this tells you that the ratios of gamma 2 by gamma 1, it can give you tan 2 phi, where phi is the angle made by the major axis of the source with respect to the x-axis. So this defines what exactly is the distortion that gets imprinted on a source which is circular. Right? It becomes an ellipse. And if you know gamma 1, gamma 2, then you can figure out what is tan 2 phi, and then figure out the angle at which you will get the major axis. That will be, you take a tan inverse of gamma 2 by gamma 1, and then divide by 2. So this tells you how you can map out gamma 1, gamma 2, the whole shear field, which is not a scalar, right? At every point, there is a direction to this field and an amplitude to this field. And so you can figure both of these things out by looking at the ellipticities of these objects. Okay? So let me show you give you some flavor of numbers, right? So because it's a little bit non-trivial because it has this 2 phi kind of relation. So it's not it's not a vector, and so it is not easy to visualize sometimes, especially the first time you are hearing it. So let me show you what a galaxy looks like if it has a gamma 1 which is greater than 0 and gamma 2 which is equal to 0. In that case, that galaxy will be oriented like this. The major axis will be along the x-axis and the minor axis is along the y-axis. If instead gamma 1 is negative and gamma 2 is 0, then it means that the galaxy is oriented in a vertical manner. Okay? Now you can consider the other question, which is what happens if gamma 1 is 0 and gamma 2 is greater than 0 or gamma 2 is less than 0. In that case, the galaxy is oriented at 45-degree angle because of this 2 phi. Okay? Because tan will become infinity, right? And that's when 2 phi is equal to pi by 2. And so phi should be pi by 4 in that case. Right? So you see gamma 2 greater than 0 and gamma 1 equal to 0 means that it should be oriented at 45 degrees, while gamma 2 less than 0 and gamma 1 equal to 0, it should be oriented minus 45 degrees. So this is shown here, what are the different components, gamma 1, gamma 2, and you can study these kind of figures in order to understand how these different gamma 1s and gamma 2s, what are the different orientations of the ellipses that you will in these different cases. Okay? Now let's try to understand what is the kind of ellipticity pattern that you imprint on galaxies, that masses imprint on galaxies. So in order to look for those kind of patterns, first we have to understand what they look like. Right? So let's consider some source galaxy population which is completely circular. Okay, this is for simplicity. Now, so this is shown here on the left-hand side with these green dots. All of them are perfect circles. Now let's put a lens in front of it. So when you put a lens in front of it, then the shapes of each of these galaxies, it changes. And you can see that the pattern it imprints, it looks something like this. The thing that jumps out, the first thing that jumps out is if you are closer to the center, the distortions that you get are larger, right? This we knew, this was obvious. Nearer to the cluster center, you used to get big arcs. Right? So you can see as you're closer to the cluster center, you get these larger distortions. And as you move further away, the distortions are smaller. This is the first thing to remember. The second thing is the pattern of the ellipticities that get imprinted. So if you have a circular axially symmetric mass, then it introduces a tangential ellipticity pattern. So all the shapes get oriented tangentially with respect to the mass that is kept at the center of this distribution of galaxies. So these kind of patterns, if you look for them, if you see these kind of patterns suddenly in the shapes of galaxies in the sky, then you know that there should be some mass here which is causing these patterns. The problem behind all of this is that background galaxies are not inherently circular, right? So if you look at intrinsic galaxy shapes, you know that they are not circular, right? There are many spiral galaxies in the universe, and depending upon the inclination angle of these spiral galaxies, they will appear to be elliptic, right? Not, I mean, their isopods will appear to be ellipses, right? And so this, for example, is a galaxy which is edge on, right? While there may be galaxies which are face on, and then they might look circular too, right? So galaxies themselves, they are not inherently circular. So this causes a problem because now when you measure the shape of one galaxy, you cannot infer really what is the shear at that location because that shear is contaminated by the intrinsic shape of the galaxy, which is not circular. Right? So that's why what you have to do is you cannot use this method of measuring the shape and inferring the shear on a galaxy by galaxy basis. Instead, you have to do it statistically. So what do I mean by statistically? You take many different galaxies, say suppose in this particular patch, right? And you average out their ellipticities. Then what will happen is if these galaxies are completely unlensed, when you average out these ellipticities, because galaxies on average will be completely randomly oriented. And so when you average it out, the average ellipticity intrinsically of these galaxies should be 0. But when there is a mass which is causing the lensing, and now you average the ellipticities of these galaxies here, you will see that the average ellipticity will be aligned in this particular tangential map again, with respect to the center of this mass distribution. Okay? So you do it here, you do it here, you do it here, you do it in different locations, and that will allow you to figure out this coherent pattern of ellipticities which gets introduced because of lensing. This happens because these galaxies are almost experiencing the same potential from these central objects, right? And so that's why they are sheared coherently in a coherent manner. And that's the reason you can statistically average it out and then figure out what this shear is. So by all this, you must have understood now that the most important thing for weak lensing is then to measure the shapes of galaxies, right? And so the question is then, how do you measure the shapes of galaxies, right? So we get these pretty pictures. In fact, the actual galaxies for whom we measure the shapes are even dirtier than what you're seeing here, right? But let me show you, to begin with, show you a galaxy where at least you can see the galaxy properly, right? And it's well measured. So the first thing to measure the shape is to figure out where is the centroid of this galaxy, right? So in order to measure the centroid, you can calculate it using moments of the surface brightness distribution. So you take as the surface brightness distribution and you take the first moment of it. So multiply it by theta, integrate over the entire plane of the sky, typically over a small region which contains the light from the galaxy. And then you divide by the same factor, right? d2 theta I of theta. This qi is just some weight function which tries to downweigh the intensities which you would have measured with very low signal to noise ratio, right? So further out from the galaxy center, you don't want to give too much weight because it's noisy, right? And so that's all what this qi is doing. Right? But otherwise, it's just the first moment to measure where is the center of this galaxy. Once you have measured the center of this galaxy, then with respect to this center, you can measure the second moments of the surface brightness distribution. So that is what is shown here. You again do I of theta times qi, and this is the weighting function. And then the second moment that you are measuring will be theta I minus theta I bar, theta j minus theta j bar. Right? So this second moment again will be will have 4 components, right? Because you can do theta 1 minus theta 1 bar, theta 1 minus theta 1 bar, or theta 1 and then j might be 2, then I becomes 2, j becomes 1, I becomes 2, j becomes 2, right? So all these ij, they are taking all sorts of indices 1, 2, right? And so you get a 2 by 2 matrix again for the second moment measurements. So once you've measured these second moments, you can define the ellipticity in this particular fashion. Okay? So what is this number? So q11 minus q22 plus 2 times iq12 divided by this this kind of complicated denominator that you see. But let's try to simplify and try to understand. Let's suppose you have a galaxy which is completely Gaussian, and this Gaussian is oriented along the xy axis. Okay? Let's suppose that that is the case. In that case, this term q11, it will tell you what is the sigma square along the x direction, while q22 will tell you what is the sigma square along the y direction. Okay? So the sigma square is giving you some information about the width of this object, right? And that's why this q11 minus q22 will be equal to a square and b square, right? Where a and b are the major and the minor axis. And so these things are related. The moments are related to these to the size of these major axes and minor axes. And then q12 will be exactly equal to 0 because you are integrating along one axis and then along the other axis. So that will give you 0. And now what you will do again is now let's consider the denominator, which is again a square plus b square. Right? And so you have a square minus b square divided by a square plus b square. That gives you a minus b divided by a plus b. Sorry, this is a square plus b square plus 2 times A times B, right? So this you can write it down as A plus B the whole square. And so this A square minus B square divided by A plus B the whole square, that will give you A minus B divided by A plus B. That quantity is just 1 minus the axis ratio divided by 1 plus axis ratio. 1 minus B by A divided by 1 plus B by A. And if you remember, 1 minus B by A divided by 1 plus B by A, this was related to the actual magnitude of the shear, right? So if you can measure the shapes of these galaxies, you can measure the magnitude of the shear by looking at these second moments and defining an ellipticity which looks like this. Okay, good. Now, as I said, galaxies are not circular even without lensing, and so they have intrinsic ellipticities, but they are expected to be randomly oriented. So if you average out many galaxies, then you can figure out what is the actual shear at the location of these galaxies. Right? So you can ask, how is the intrinsic ellipticity of sources related to the observed ellipticity and the shear at the location of the galaxy? Okay. So this involves some matrix algebra, but it's again not too complicated, and you can show that this actual intrinsic ellipticity of the source is related to the observed ellipticity of the source and the reduced shear with these particular equations. And now, if you average over intrinsic ellipticity, we know that when you take that average, you should get 0. And so you can now average the intrinsic ellipticities here, and you can show that the average of these observed ellipticities then is equal to either G or 1 over G star, depending upon whether your modulus of the shear is less than or equal to 1 or greater than. This particular quantity is of less interest because this happens very close to the center of the cluster. So we will not be considering this particular part, but it's mainly this particular equation that gets used, right? So you take the ensemble average of the observed ellipticities of galaxies, and it tells you what is the reduced shear at that location. And if we are in the weak lensing regime, the reduced shear is same as the shear at that particular location. Okay. Okay. So now that we have many galaxies, we have made measurements of the shapes of many of these galaxies. We know where they are oriented. Then we can figure out what is the value of the shear and what is the orientation of this shear. So we know exactly what the value of shear is at different positions on the sky. Right? We have done an ensemble average of a few galaxies in a certain small region and then calculate what this value of shear is. Now, how is that shear used? Right? That shear is being caused by matter distribution in between. So let's try to figure out how to infer that matter distribution from the observed shear. In order to do that, we have to start from the equations that we actually learned before in the first lecture, right? So one of the things was there is a relation between the lensing potential psi and the kappa value, which is the Poisson equation, right? So you had Laplacian of psi is equal to 2 times kappa. Now you can take psi, which is this lensing potential, and you can decompose it in Fourier space, right? And so the Fourier expression will look something like this. Psi tilde of L is equal to integral of d theta e to the minus I L dot theta times psi. So you can do a Fourier decomposition again in 2D, right? So that's why you have this minus L bar dot theta bar, right? And once you start with this equation, now you apply the Laplacian on this, right? Then you get a minus IL down, and then you apply, you take the gradient, then you get a minus IL down. You take the Laplacian, you get another minus IL down. And so in the end, you get minus mod L square on the left-hand side, minus mod L square times psi of L. That's what the Laplacian gives you. And that is equal to 2 times kappa. And so again, you're taking it in Fourier space. And so that's why it becomes 2 times kappa of L. This minus sign, which was here, I just took it here. That's all. Okay? So this is the Fourier space equivalent of the Poisson equation. Good. So how does this help? Let's go through it again slowly. So we also have the definition of what gamma 1 and gamma 2 is with respect to the lensing potential. Right? That definition was given by these two quantities. These were derivatives in the lensing plane. Right? So this is the psi 1, 1. So you take along the x-axis the derivative of the lensing potential 2 times, right? Del 2 psi by del theta 1 square, and then subtract del 2 psi by del theta 2 square and take half. That is what is gamma 1. Gamma 2 is just del 2 psi by del theta 1 del theta 2. So this is the definition of what gamma 1 and gamma 2 looks like. Right? And the shear mod gamma, that you can write it down as gamma 1 plus I gamma 2. Right? So now that we have this Fourier equation for or we are doing things in Fourier space, so we'll express this psi 1 1 also in Fourier space. So when you take this derivative with respect to theta 1 or along the first direction, the x-axis direction, then you get a L1 square. And here, if you do it, then you get L2 square. Okay? So what you get in the end is L1 square minus L2 square divided by 2. That's exactly what you are seeing. There is L1 square minus L2 square divided by 2. This comes from this component. And then psi 1 2, which is related to gamma 2, you can imagine it gets L1 times L2. Okay? This I we have just put in by hand to just separate the components for the shear. Okay? So now you have what gamma looks like in terms of the lensing potential. But this lensing potential is related to kappa by this Poisson equation. So now you can take this mod L square down, right, and replace psi of L by kappa divided by mod L square. Okay? So you now get an equation between shear and kappa, but in Fourier space. Right? And it looks something like this. You can also take this quantity and move it to the other side, and you can see that kappa of L is also given by 1 divided by mod L square times again this kind of a kernel multiplied by gamma of L. Okay? So if you know kappa of L, you can predict what is gamma of L. If you know gamma of L, then you can predict what is kappa of L. Okay? So it's a simple relation between kappa and gamma, which allows you to go from one to each other. The relation is much easier in Fourier space than it is in real space. Okay? And you can also see there are many similarities between the two, right? Except for this plus I going to minus I, there is no difference between these two equations when going from one to the other, right? Kappa to gamma and gamma to kappa. Okay? So this also helps us to write down what is finally the equation going to be for kappa. So if you have measured gamma, you can put it on a Fourier, you can calculate it as in the Fourier domain itself. If you have computed the shear in the Fourier domain, you apply these equations, you can get the convergence in the Fourier domain. This is just sigma divided by sigma crit. And so if you know all the lens source distances, etc., you can figure out what is the surface density. Okay? So that's how you can go from measured values of shear to measured values of this quantity kappa, which is related to the surface density. Okay. Now, let's go one more step back to figure out what is the relation between the potential and kappa, but in real space. Okay. For that, you should consider first the equation for the deflection angle, which you get by taking the gradient of the potential. That's why it's psi I. Okay. So that is 1 over pi integral d theta prime kappa theta prime, and this kind of deflection equation that you are used to. If you are for a point mass, you can see this, that it looks like 1 over mod theta. Right? It's just towards the direction of that point mass. Okay. So this is the definition of psi. Then you can take another derivative, so you can work out what is psi ij. It will look something like this. You can see this Dirac delta function coming because there is a theta I here, right? And so on. So you can go through these equations and show that this is indeed the case. And we have the definition of gamma based on these derivatives of the potential, right? And so you can use these equations, gamma 1 and gamma 2 equal to this. You can substitute I and j for 1, comma 2 into this equation. And you can write down the relation between gamma and kappa in real space as this particular quantity. So you see, gamma is related to is some sort of a convolution integral of a kernel with the surface density or with the convergence. So this is a convolution operation, right? Because I have an integral over some variable, I have a kernel which is theta minus theta prime, right? And then a surface density, another field. So convolutions are typically simpler in Fourier space, and that's why you just saw multiplications in Fourier space when we saw these equations. So that's why you can go from one to the other, and in real space it should look like a convolution. Okay? And that's exactly what you do. Now, given that the relation in Fourier space for gamma and kappa, it looks fairly similar, you can also expect the relation in real space between kappa and gamma to also look similar. And that's exactly what happens. So the only things that change, this theta 2 square minus theta 1 square remains the same. Instead of minus 2i theta 1 theta 2, we just have 2 times theta 1 theta 2. Okay? Remember, I've written this as a vector. I could have easily written theta 2 square minus theta 1 square plus I 2 theta 1 theta 2. It's the same thing. So you can go from gamma to kappa by doing this convolution. You can go from kappa to gamma doing this kind of convolution. That's all. So you can reconstruct what is the mass density in between us and the galaxies by measuring the shear itself and using these equations. So this is quite powerful. Now there's another quantity which is very important. You remember, if there was a point mass at the center of an unlensed distribution, then the galaxies, they get oriented in a tangential manner. Okay? So rather than figuring out all the shears at each and every location in order to reconstruct what the kappa is or what the surface density is, you can do another clever thing, which is you go to the center of this galaxy, center of this mass distribution, whose mass you want to compute, right? And you can look at the ellipticity in a tangential manner. So instead of averaging over a square like this, what you can do is average over all galaxies which are expected to have roughly the same tangential shear, right? So when you do that, then you are getting a high signal to noise ratio measurement of the tangential shear, and you are averaging over galaxies which are expected to have roughly the same shear. Right? So for an azimuthally symmetric distribution, you can show that when you average the tangential shear, so the shear which is oriented in the tangential direction, right? So you can define a line from the location for whom you want to measure the shear and the galaxy and figure out what is the tangential direction and reorient your axis along the tangential direction. So that will allow you to figure out what is the tangential shear. Right? So that tangential shear averaged over annular, this is related to the surface density within that radius. So surface density averaged within the radius minus the surface density at that radius. So you have surface density averaged over this entire disk here minus the surface density at the location of the outskirts of this disk. So you measure this shear, and that is what it is related. Now this is easy to show in terms of an azimuthal symmetric distribution of matter, but if you use a divergence theorem and you can show that in fact this particular aspect of averaging the shear along symmetric like circles, right, is something which is very special. It allows you to compute and to show that the average tangential shear when averaged along the circles is related to the average surface density within that circle minus the average surface density at that location. Whether it's an azimuthally symmetric distribution or not, still this kind of theorem holds. Okay? So there are lots of similarities again between the 3D gravitational potential. You know, in the case of 3D gravitational potential, there are these things like shell theorems, right, from Newton, and so there are similar kind of things which are also true uh, for uh, for the deflection angles and so on in lensing. Okay? So this particular aspect again, it can be shown using the divergence. So if you have these two different ways, then now you can see that you can either reconstruct the full map of the sky, or you can reconstruct the mass distribution around some object, say a galaxy or a galaxy cluster. You sit at the center of it, and as a function of the distance away from the galaxy cluster, you can measure what is the shear which is imprinted on these galaxies. Right? So these two different methods, it allows you to see the unseen, right? So see something which is very hard to see, like dark matter. But before you get to these kind of good results, you have to realize that the real world is quite dirty, right? So when you take an image on your iPhone or your Android phones, right, you get quite clear images. The reason why you get clear images is because the photos that you are taking are typically in sunlight, right? And so the subject itself is quite bright. But when you try to take a picture in the dark, you can see it looks all very green, right? And a similar thing happens with when we are trying to image galaxies which are very far away, right? The number of photons coming from these objects is so small that it gives you a very grainy picture. Okay? And you can see some of these grainier pictures as captured using CCD chips, which are similar to the ones that you have on your phone, but they are quite sensitive chips. Okay? So these are CCD chips which are very sensitive, and they are also much bigger compared to the chips that are present on your iPhone or Android. Okay? So you take these chips, you take a picture with these chips. You can see many, many bad things, right? One of the things is, for example, there is a bad column here, right? So it's all black. Of course, the sky is not black like that. So this is just a CCD column which has gone wrong, okay? And that's why it just gives out zeros. There's another CCD column here which has gone wrong. In addition to that, you can see some bright stars here which blow holes, right? You can see the saturation trails from these bright stars. You can also see some diffraction spikes. There's bleeding. Sometimes you see satellites, artificial satellites, which were launched by us, going through your field of view. Some of them, like the ones sent by Elon Musk, they just like start to go through and bleed a lot on the images. Right? So you can have these kind of things. You can also have things called chip gaps. So between each of these chips, there will be small regions which the camera is not able to capture. And this happens because you cannot put all these CCD cameras just adjacent to each other. And so there is a small gap which remains. And that gap, you cannot see anything when you just take one picture. So imagine tiling one picture by using many uh, uh, photos that you get. Right? That's exactly what a telescope does. Okay? Then in addition to this, there are cosmic rays, bad pixels, many bad things that happen. You can see also differences in the sensitivities of each of these CCDs. Right? And so they're also being operated at different bias values and so on. So there's a lot of complications that go in. So you have to correct for these effects. Then if you go to longer wavelengths, sometimes what happens is the light which is coming from above, it enters your CCD, and not all of that light gets absorbed and gets converted into electrons, but some part of that light reaches the back CCD and the back of the CCD, and it reflects back from there. So when it reflects back from there, then it can interfere with the light coming from the front. Right? And so that results in this kind of interference fringes that you see. And so these are also things that you need to just take out, right, and remove. So there are lots of complications before you go from the dirty pictures that I showed you to the pictures that look like this, where you can at least see the stars and some of the galaxies and so on. But you can see how bad they look compared to the Hubble pictures that you're used to. Okay? So we try to measure the shapes of galaxies which look like this, sometimes even fainter, which look like this. So what do you do when you have chip gaps? When you have chip gaps, in order to fill these chip gaps, you just do a dithering, right? So you move the telescope a little bit so that the chip gaps fall in a different region of the sky. And when you co-add data from all these different detectors, the chip gaps get filled. There will be some common region which doesn't appear in both. And so you cannot just do one dithering, you have to do multiple dithers so that you don't have many gaps which remain. So that is what is done. And then finally, you get this kind of map of galaxies. Now, these galaxies are what you want to measure their shapes for. And so you cannot just have the map, you also need a variance map, which means you need to know what is the error bar on the intensity in each of these pixels. So that is done by something called a variance map. And in the variance map, you can see like how many different CCDs have gone. If less number of CCDs have gone, then your variance is larger. If more number of CCDs have gone into the co-addition of these images, then you see less of noise in those pixels. So you have to account for all of these issues before you go and measure the shapes of galaxies. So let me show you the kind of galaxies for which we measure the shape. Let's suppose the original image, let's suppose you had a telescope in space with very good angular resolution, it will look something like this. There is a lensing shear, and mind you, this is quite a large lensing shear of 0.2 that you apply to this original image, then the original image gets distorted like this. After the original image then comes through the atmosphere, there is blurring due to the atmosphere. So then immediately you see something which looks like this. Of course, you still don't see what comes from the atmosphere. What you see is something which gets detected on your detector. Right? So on your detector, because of pixelization, you will see this pixelized version of the atmospherically blurred galaxy. Right? But it is also not what falls on the pixel, but what you measure is what the detector measures. Right? And so there is also additional detector noise that gets into it. Right? And so you see that this what you measure in the end is this noisy shape of the galaxy, and you want to infer what is the shear at the location of that galaxy. Right? So you can see only a few pixels have lit up, and so we have to typically work with galaxies that look like this. Okay? And what we need to do is, this is the process in which nature does the things. What we have to do is reverse engineer, which is take this detector noise or take this image which has all these components and then figure out what the lensing shear is. So it's complicated. So in the last few minutes, I wanted to show you some of the big surveys which are being done currently, weak lensing surveys, in order to map out the dark matter distribution in the universe. So there are a number of large area deep imaging surveys. There is the kilodegree survey. This was one of the first of the bigger surveys that are going on. This kilodegree survey is panchromatic, which means it has many, many different filters in which it observes the galaxies. So it allows it to figure out precisely which galaxies are located where. That allows them to do very good tomographic reconstruction of matter. Right? Then there is dark energy survey, which goes shallow but wide, and it goes out to roughly 5,000 square degrees. Right? It covers it in only few bands, but it is deeper than the kilodegree survey. Right? And then finally, there's the Hypersupply Cam Survey, which I work on. It is the deepest among these three surveys. So it goes quite deep, and but to compensate, it only covers a small area. Right? So it allows it to map out the dark matter distribution out to further and further away distances, because as you go deeper, you see galaxies which are fainter and fainter, which are further and further away from us, right? So these three surveys, they have their own niche and their results are complementary to each other. And then there are many surveys which are also planned in the future. There's the Legacy Survey of Space and Time, done by the Vera Rubin Observatory, LSST, right? So this will start around 2024. Then there is a mission which is going to be done from space. It's called Euclid. By now, it should be obvious why space is better than doing things on ground, right? Because you get the image which is not blurred by the atmosphere, right? But it also has its cons because you cannot put such a big mirror, like LSST has a bigger mirror, so it can see even fainter galaxies. While Euclid, because it's in space, it can see them much better. But the area of the telescope is not as big as the area of the LSST. And then finally, there's also this thing called W first or Roman. And so there are multiple surveys which are also being planned for the future. So let me show you one of the results coming from these surveys. So this is the Subaru Hypersupply Cam Survey. And now what I'm going to show you is those equations that we derived, but in action and what it allows you to do. Right? So we have measured the shapes of galaxies in different redshift bins. So as there are some galaxies which are nearer to us, some galaxies which are further away to us, right? So these galaxies are the furthest away. These galaxies are the closest to us. Right? Now let's go slowly behind it because you see that these are not galaxy maps, right? So what I'm doing is the following. I take small cells, so these are regions on the sky. I divide it into small rectangles, like square pixels. In each of these pixels, there are many, many galaxies. I take these galaxies, I measure their shapes, and then I average the measurement of this shape. When I do that, I get an average shear, which has an amplitude and a direction. So that is what is shown here in this particular map with the lines. Okay, you can see some white lines on this map. Those white lines tell you what is the average ellipticity direction of the galaxy and the magnitude of that ellipticity at any given pixel which falls in our survey area. Okay. So those are the white lines. We have done it for galaxies which are very far away. Then we have done it for galaxies which are midway, roughly midway in between, then even closer, and then further closer. Then once you have the shear field, which is mapped on the sky, then we can use the equations that we derived to go from gamma to kappa to get what is the projected surface density of objects which are roughly halfway in between. Right? So you look at this map of those lines, and from there you can figure out what is the dark matter or the matter density distribution. So that matter density distribution is shown in colors here. The black portion is where there is less of matter, and that's why it's black. It's devoid of much dark matter, while the whitish portion that you see here, there's a lot of matter there. Okay? So you can go from these kind of maps to work out matter distribution at different locations. And so here you are seeing a tomographic reconstruction of dark matter. Okay? One of the things that again you can see from this map, which is very obvious, is that in the early universe, the structure was not so inhomogeneous compared to in the latter universe. Right? You can see there are a lot of fluctuations in the latter universe compared to the fluctuations in the early universe. So what you are mapping out is the growth of density fluctuations in the universe by using this particular technique. Right? So you can compare how these fluctuations are growing as a function of time with numerical simulations of dark matter with different cosmological parameters. And the simulations which give you the match, the right match to how the growth is happening in your observations, then you can get constraints on the cosmological parameters. So that's what is shown here. This is the matter fraction in the universe, omega matter on the x-axis, This is sigma 8 on the y-axis, which tells you how clumpy the universe is. And you can see we get these kind of results. This is the results from HSC. There's a result from DES. There's another result from KIDS survey. All these three results are consistent with each other. And then there is this result from the CMB analysis of the same, of not this data, but of the CMB data. And that gives you results that look like this. So you can measure these quantities and you can compare each of these models with each other and learn about the cosmological parameters. In addition to this, you can also learn about the masses of galaxy clusters and so on. So let me not just go into this right now. You can ask me questions about this. So this is where I wanted to stop. Right? What I showed you is how you can use gravitational lensing to do many, many things. Right? And we have just scratched the surface. I've told you how to measure the cosmological parameters of the universe. You have seen from Anuprita's talk how you can understand the galaxy dark matter connection. I didn't talk about the tests of general relativity, but you can also do them. You can understand nature of dark matter, so on. So there are a variety of things that you can do. So gravitational lensing is very powerful. And I hope that I've given you a reasonable introduction for you to then start off and go into this particular field. There are a number of references from where I've borrowed some of this material. You can take a look at the reference slide for this, is the slide. Okay. So with this, I will stop here and take questions. Thank you. So I've opened my chat box, and participants, you can go ahead and, yeah, Safiq, do you want to go?
What about this microlensing? Is it
Right.
same as this weak gravitational lensing?
Right. So we did not cover microlensing in this particular talk. So microlensing is a special form of strong lensing where you form multiple images, but these multiple images are separated by a very small distance. Right? So if the image separation between these different images is of the order of micro arcseconds, right? And then now you're observing it, say, from the ground, right? Where the scene or where the atmosphere is blurring all your pictures, right? And so because of this blurring, all these images, they get merged into one. And then you just see one image, but because there are multiple images, the brightness of that image is much larger than the original brightness of the source. Or the flux coming from those images summed over, like in total, will be much larger than the flux coming from the original source. And so that is what is microlensing. Typically in microlensing, you may have objects which cause the microlensing to move with respect to the source. And when this motion happens, the exact impact parameter between the source and the lens, it changes as a function of time. And so these multiple images, they form and then they go away, right? And so you see the magnification increase and then start to decrease again. So that is what is microlensing. And it is also powerful. It's just in the interest of time, we could not go over. Okay? Does that help you?
Okay, fine. We get an idea.
Sure. Yeah. So you can take a look at these links, and the slides are linked here. You have a tiny URL which goes back to this, and you click on this link, you will be taken to the microlensing lecture notes from the ISSAA lecture series, and you will find lots and lots of material there, like how you can use microlensing to find exoplanets, for example, or to learn about the nature of dark matter, etc. So I encourage you to look at it. I see a hand up from Pushti. Please go ahead. You can unmute.
Hello, sir.
Yeah,
so
hi.
My question regarding to weak lensing survey, as the presentation showed that one the plan for future, it can give the widely range of infrared space telescopes. So James Webb telescope is considering it or not?
Oh yeah. You mean will James Webb go out of fashion and so on? So of course, James Webb Space Telescope has a limited lifetime as well, right? They are trying to extend it as much as possible. But W first is going to be, or Roman as it's called, is going to be the decade after, so the next decade. Right? And James Webb Space Telescope has a very small field of view compared to W first. So W first is meant for doing large surveys of the sky, while James Webb Space Telescope, even though its field of view is larger, but it's not as large as W first. So if it wanted to do a survey like what Roman or W first is going to do, it will take lots and lots of time for James Webb. Does that help?
Yes, sir. Yes.
Yeah. So all of these telescopes, they typically have a different niche, and so that's like they don't try to build the same kind of telescope and put it in the same manner, because typically the science that has to be done, or at least the most exciting kind of science, it comes out in the first few years of the new instrument that goes up, right? And so they always try to find a different niche for each of these telescopes to operate in. Okay, there's a question in the chat box, so let me take it first. Pushti, if you are done, then you can lower your hand. Thank you. So one of the questions is from Amit Mohan Rakshit in the chat box. How can you so surely distinguish between an image and a real source? You can never distinguish between an image and a real source. What you see is only the image, always, right? Because everything that you see is always going to be lensed. It may not be strongly lensed, but it will always be gravitationally lensed, right? Because there will be some sort of weak lensing going on because of all the matter that is in between that object and the image, right? And so there is no question about distinction, because you cannot distinguish what is an image and what is a real source. You only see the image. Everything that you see is kind of a mirage, right? But you see these distortions, right? And these distortions are the things that you can pick up. Right? Just like that lady that I had shown you before, right? If you did not have the picture of the original lady and only the images in the mirrors, you would still say something is funny, right? Just by looking at that picture. And if you knew typically what a person looks, right? And so you can tell what is not strongly lensed and what is only weakly lensed, for example, right? Just by looking at how big these distortions are. Okay? And in the end, what we are doing is we are not really measuring we are measuring the shapes of galaxies. But from these shapes of galaxies, what we are interested in is measuring the shear which is imprinted on these galaxies, right? So you have to average many of these shapes of galaxies to then figure out what the true shear is, because all of these galaxies, they get coherently distorted. So it is the coherent distortion that you try to figure out. I hope that helps. And then there is a question by Shubhadeep Datta. He's asking whether is there any general data or data available for any public researchers or students like us, using which we can study further? Absolutely, yes. Each of these surveys that I've mentioned, the dark energy survey, the kilodegree survey, and the Hypersupply Cam survey, they have data which is made publicly available. So you can take each of these data sets, you can do all these analysis by yourself. Okay? So just recently, I had given a set of lectures for the Indian Association for General Relativity and Gravitation. These set of lectures were on weak lensing specifically, although I do cover initially a lot of basics of gravitational lensing as well. And there were associated tutorials with it. So in those tutorials, we covered how you can go from the shape catalog from Subaru HSC to measure the weak lensing signals like the ones I had shown before. So absolutely, you are more than welcome to take a look at this data, go through it, try to analyze it, try to reproduce some of the results from these different groups. You should definitely do that. Okay. Any other questions? Debarti, maybe if in case you are there, is there anything on YouTube? Okay. If not, I guess we have gone over time by 10 minutes. Santosh, maybe you can announce when the next lecture is going to be. Santosh? Okay, I guess you guys know when the next lecture will be. So I will just stop here. Okay. And if you have more questions, please feel free to ask about it. Hello, Santosh, can you hear me? Okay, I guess he's not around. So I will stop my video and stop sharing the screen. Yes, yeah. Yeah, so I was saying that can you announce the next lecture when it's going to be? And I have paused the recording. Yeah, yeah, okay, great. So there is still some time. People are asking in the chat to give the location of this tutorial set and the lecture series. So the lecture series will be made available